Hello, my name is Ananya Joshi, and today I'll be presenting our work on outlier ranking in large-scale public health streams. This work was done in the Machine Learning and Computer Science departments at Carnegie Mellon University, and with the Delphi Research Group. Delphi is a public health data curator in the United States, which means that they receive data from a number of providers and make it available at different geographic tiers like counties or states or the nation as a whole. This data is also updated frequently, in most cases daily, so it forms data streams or time series data. Overall, Delphi processes large volumes of geospatial data streams, often hundreds of thousands of these data streams. Experts in Delphi are responsible for reviewing these data streams, and they look for outliers that signify changes in data quality or disease dynamics. And so in a data stream, they might look for unusual changes, which signify a COVID wave, zero cases, which suggests inaccurate or delayed data, or when this data went from being reported every day to only once a week. These streams have some notable properties for outlier detection. They are often non-stationary because of disease dynamics, they are noisy, and they might have limited history. Now, these outliers are a bit subtle to identify, and historically, experts manually looked for them. They were able to do so because these streams have at least some data history, they usually only have a few outliers, and they have high temporal dependence and some geographic dependence, which means that the stream of COVID cases in Pennsylvania might be similar to the stream of COVID cases in New Jersey because those two regions are geographically close. Now, to help experts identify outliers in this large volume of data, an initial approach was to use univariate outlier detection, where we applied this method per stream. First, we predict a value, then we calculate a difference between the observed and the predicted value, which we call a test statistic. And then we can either use the historical test statistic distribution, a 99th percentile, for example, to identify a threshold and see if the test statistic is greater than that threshold, or we can use this historical test statistic distribution to calculate a p-value. And then you have a value between 0 and 1 that you can use to rank outliers. Now, the first half of this approach can be tailored per application, and we're really going to be focusing on the second part, which are what we call outlier identification mechanism. Now, the problem with the univariate outlier detection method approach is that it returns far too many false positives when it is applied to large scales of data, like hundreds of thousands of public health data streams. And just to recall, we have a lot of data in Delphi, and we have these two existing methods to identify outliers. And using the first method, we return 144,000 outliers around per day, which is far too many for an expert to analyze. And in the second approach, even when we've modified it, it still returns 14,000 data points that are ranked as the number one most important outliers to investigate per day. And the problem here is that experts can meaningfully distinguish between these points that are tied at number one. And there is a reason for this. It's because the historical test statistic distribution is not meant to be used in this way. We shouldn't be comparing the test statistics across different data streams and using those to rank outliers. And we also shouldn't be using older, limited, and non-representative data for this historical test statistic distribution. This leads to a new machine learning task, which we call multi-stream outlier ranking, where the objective is to rank the overall highest priority outliers across all data streams using outputs from any univariate outlier detection method. So we have our input data streams, we have any univariate method and the resulting test statistics, and then we have the ranking method, which is supposed to produce a ranking of the outliers from these different data streams. Now, the benefits of this approach is that it can be used for large-scale data streams that should not be directly compared to each other, like noisy, non-stationary streams that are subject to different dynamics. It also helps prioritize expert attention from these outliers so there aren't 14,000, let's say, outliers that experts had to go through per day. This task is relevant in other domains like fraud detection, Internet of Things, and industrial quality control. So our approach for this task is to rank the most extreme outliers across data streams, and it's different than the existing outlier identification mechanisms because even though they account for the properties of data streams in public health, because of the limited history specifically, the histogram of historical test statistics is limited. There are only a few observations that pepper this distribution, and there are no observations in this case between, let's say, a test statistic of 0.4 and 1. So there's no way to distinguish a test statistic of 0.6 versus 0.8 versus 0.9. And to address this kind of issue, we use the block maxima approach from extreme value theory, where the idea is if you have an infinite stream of, let's say, test statistic values, and you create different blocks, and you take the maximum value per block, these maximum values should create a distribution which has more observations at the extreme ends. And so the problem here is that this approach traditionally needs long streams of stationary IID data. But in order to address this problem, and instead of just using maximum values from blocks across time, our idea was to create blocks across time and data streams. So we grouped together data streams by where they fell in this geospatial hierarchy, which consists of counties, HRRs, which are hospital regions, which consists of multiple counties, states, HHS regions, which consist of multiple states, and the nation as a whole. And we can use sibling streams, which are streams that have the same parent in this geospatial hierarchy, to create spatial groupings across streams. So in this way, we can create blocks that have both a spatial dimension as well as a temporal dimension, and then select the maximum values from these blocks. So our approach, once again, is to create blocks across streams and time. And the benefits of this approach is that, because of this intuition that we can increase the granularity at the top of the historical test statistic distribution by using the recent maximum values across all regions, we can also have an approach that works across data revisions, and all data points are compared to the same historical test statistic distribution. And we only need to use recent data. So our results for this approach, which we call outshines, show that our approach ranks better than the prior alternatives. And we tested this using a survey which used the outliers that were tied using the modified ranking approach, the previously best method. And 17 experts took the survey, which is over a 5 times improvement from historical standards. The results show that this method, on a number of traditional outlier detection and ranking methods, performs much better than the alternatives, and this holds across different univariate methods, and we have a number of ablation experiments in our paper. We also wanted to highlight the deployed evaluation of outshines because it demonstrates the practicality of this approach, and both this and the prior set of experiments were pre-registered before any data was collected, and they were IRB approved. And so we compared our approach to a baseline of volunteers who met weekly to manually inspect the data, as well as to the modified ranking approach, the prior best approach. So we could find that the rate of expert-identified outliers with outshines was much higher than the baseline of weekly volunteer review. And there were also a number of additional benefits, like it didn't take too long to process the data using outshines, or that there were far fewer ties, 21 versus 14,000, using outshines versus modified ranking. And finally, experts were able to find the outliers that they cared about 9 times faster than the baseline and 4 times faster than with modified ranking. And this metric really refers to the precision of this method. To conclude, we just have a few takeaways. First, we identified this task of multi-stream outlier ranking because many large-scale streams processed using univariate methods have too many ties to be meaningful. Our task approach, outshines, explicitly addresses existing task limitations, especially those that stem from the historical test statistic distribution. Specifically, for Delphi's public health data streams, outshines first outperformed other approaches on standard metrics in the expert evaluations. It also provided Delphi the first ever insight into the outliers that were worth investigating on a large scale. And finally, reviewers were able to identify outliers 9.1 times faster with outshines than without. Thank you so much for your time. Please check out our paper, and you can email any of the authors if you have any questions. Thank you.